This is a video for AQA Further Pure Mathematics. Hyperbolic functions section 2.6, further differentiation and integration. Well, we can use what we know about sine and cosh and their derivatives to work out the derivatives of Tanchecks and Tanchecks. This is similar to the working out the derivatives of tan and sec with the trig functions. So for Tanchecks we can think of that as being equal to the derivative of sine x over cosh x, and then use the quotient rule. So the quotient rule says that we take the bottom line cosh x and multiplied by the derivative of the top. Derivative of sine is cosh, so we get cosh x, and then subtract the top line sine x multiplied by the derivative of the bottom line cosh x, and the derivative of cosh is sine, and then divide that by the bottom line squared, so cosh squared x on the bottom. Now on the top line we've got cosh x squared minus sine x squared, and cosh squared minus sine squared is equal to 1. So this is the same as 1 over cosh squared x, which of course is equal to sec squared x. So this all becomes sec squared of x. Sec x, we've got a couple of ways of doing that. One way again is to treat it as 1 over cosh x and then use the quotient rule. An alternative is to use a train rule. So if I say that this is cosh x to the power minus 1, then differentiating that by using the chain rule means that I'm going to get negative 1 and then cosh x power minus 2 multiplied by the derivative of cosh, which is sine x. That I can then simplify by treating the cosh squared in two parts. So I can say that this is going to be negative of 1 over cosh x and then sine x over cosh x. So that's taking the negative 2 and putting one of them 1 over cosh x and the other one as sine x over cosh x. So this is then equal to negative of 1 over cosh x is sec x, and sine x over cosh x is tan x. Now these are very similar to the trigonometric derivatives that you've already met, but do be careful with the signs that are involved because they're not necessarily exactly the same format. Now let's consider the integral of tan x, and we can see that that is sine over cosh, and here we've got a function to integrate which is in the form of the derivative f dash x over f of x, and we know that the integral of that is going to be natural log of f of x plus a constant, of course, so therefore the integral of Tanchecks is natural log of cosh x plus c. Well, there are other results that we can prove both for differentiation and integration, and you should have a look at these and make sure that you're familiar with the results that are quoted in your tables, because you'll have a copy of the tables that you can use in an exam. So as an example, let's look at this where we've got y equals sec x and plus Tanchecks, and we want to find the turning point on the curve. Well, it's a standard method, isn't it, to first of all find dy by dx, and we can say that the derivative of sec x is negative of sec x Tanchecks, and the derivative of Tanchecks is sec squared x. So that if we want dy by dx equal to 0 to find the turning point, this means that this expression here must be equal to 0, and we can factor out of that a value of sec x, so we end up with sec x. If I take out negative, I get inside the bracket then Tanchecks minus sec x. Well, we know that sec x can't be equal to 0, so therefore we have that this bracket must be equal to 0, and so sec x must be equal to Tanchecks. So sec is 1 over cosh, and that must be equal to sin x over cosh x. And therefore the only way that we can get that to be true is that sin x is equal to 1, and so x is equal to sin inverse of 1. Now in your formula sheet there is a formula for sin inverse of x, which is log of x plus root x squared minus 1. So make sure that you're familiar with that one as well. So your formula sheet says that sin minus 1 of x is natural log of x plus root x squared plus 1. So therefore we have here that x, it must be equal to natural log of x, which is 1, and then plus the square root of x squared plus 1, so root of 1 squared plus 1, which is root 2. So our answer is that x is equal to log 1 plus root 2. So just looking through that again, we needed to differentiate when we've got standard results for those derivatives, and then make that equal to 0 to find the turning point, so that we ended up with this expression, which meant that 1 over cosh x must be equal to sin x over cosh x, and therefore sin x is equal to 1. And again, remember that there's a standard result in your tables for sin inverse of x. So I ended up with the square root, beg your pardon, x being equal to logarithm, natural log of 1 plus root 2. And just to illustrate that, this is the curve of sec x plus Tanchecks. So this is y, and here we've got x is being equal to log of 1 plus root 2, and you can see that that indeed is at the turning point of the curve. Well, that concludes this video on differentiation and integration, and indeed concludes the series of videos on hyperbolic functions too.